All right, folks, so welcome back to Intro to Unix command line. We're going to hopefully actually start seeing lots of fun, powerful things we can do today with our coding. So hopefully yesterday we remember a bunch of stuff we learned, including file permissions, commands like cat, word count, how to redirect the output of programs and how to feed the input files into programs and how to concatenate those versus overwrite things. We discussed a little bit about piping and pipelines, and we'll talk more about that today. We talked about making symbolic links. We learned grep. We went through and learned a bunch of stuff about regular expressions, and then we moved on and learned a bit of sed also. Which is hopefully pretty useful. Today we're going to learn one more pretty nice, or a couple more pretty nice Unix tools, the first being awk. But in order to do that, we should open up our terminal and log into Hoffman. My computer lets me want to do that. Two windows. So potentially we now have a symbolic link on our own computer to log in. That'd be nice if we do, because some of this is about learning how to do things efficiently and effectively and kind of save time. Let me make my text bigger real quick. And so hopefully we can SSH and maybe just type SSH Hoffman now. And again, our password's not going to show up. That's fine. If we yesterday, do we remember how we started making interactive how to get an interactive session? I hope we do. And then maybe we save that into a text file. That would be something like if I think I named mine interactive 2 yesterday. So if we open that up, hopefully we can see that what's in there says QRSH, and then we have a time, or then we're asking for data, and here we're asking for an interactive session for 3 hours to use 2 gigs of RAM. And so you can either type this out again, or if we save this into a text file, which I hope we did, then we can actually just run that file. And we're going to kind of skip back and forth a little bit. So we're getting ahead of ourselves, but it's hopefully nice to do. And so how we run something on Hoffman is we tell it the path to what we want to run. And so in this case, it's here. And so my current directory is denoted by just a single dot / and I can type interactive2 shell. And if I hit enter, I'm going to get an error. And it's because the permission is denied. And the default, whenever you write a script, is for that script not to be executable. And so hopefully then we remember how we make that executable is using the chmod command for change mode. And I'm going to say user plus X, because I want myself to be able to execute. And then I'm going to write interactive2.shell, and it changes. Are we feeling okay? I hope. And so then if we want to execute that, it's .dash again. And you'll actually notice before I tried to tab complete typing out interactive2.shell, and it actually wouldn't let me do it. And it's because the computer is smart enough to know the .dash means I want to run a script. And because the permission on this interactive2 shell wasn't executable, it wouldn't actually even let me tab complete it, but now it will. So that's nice. And then I hit enter, and it'll take a minute because hopefully there's, 40 of us all asking for a couple gigs of RAM to be, saved for us on the Hoffman cluster for the next 3 hours. But hopefully, we'll get that and that works. Are we feeling okay right now? I hope. I'm not seeing comments come up, so I'm hoping you're with me. Are folks with me? Are we feeling, for those of us that have our cameras on? Or do we want a moment, or do we want me to really go through stuff? I don't know. How are we feeling? Okay, now the chat's doing things. Okay, perfect. All right, I'm getting lots of yeses, so that makes me happy. All right, good, excellent. Thank you, guys. And so now, like I said before, I changed from being on login 3, that node, to now I'm on a computational node on Hoffman, where I can comfortably run programs and scripts and ask for, up to 2 gigs of RAM with what I'm doing. That's way more than what we need. And we'll talk later on about how to figure out, or at least find out how much jobs are using, so we can ask for the right amount of stuff when we're talking about submitting jobs to Hoffman in a little bit. So then we're going to move on to awk. Awk is a great tool. It's both a programming language and a text processor. So it's a program. It has kind of its own specific language, and it's really great for parsing data. So awk is epic at parsing and manipulating tabular data. And so tabular data, what I mean by that is thinking about a text file that looks like an Excel spreadsheet. And so, you can save your Excel spreadsheet like a CVS or a tab delimited file. And so basically we just have data in rows and columns that are separated by spaces, tabs, commas, etc. Whatever you want to do to separate your fields. And we can parse that data in very specific, fun ways. And it just iterates through an entire file line by line. And so the basic syntax for awk is awk, action to take. You're going to tell it to do something, and then you're going to feed it a file. And that's what it expects. So really simple uses for awk would be awk print, and then you're going to feed it a file. You can say awk print, and then now we can give it a symbol like $1, and this is how you denote what column you want a file to parse. You could tell it things like awk print column 1, and then I'm putting here in double quotes. Now I remember we're escaping out or backslashing a T, so that means we're giving it a tab, and then column 3 file to parse. And so what this last command would do would print the first column, a tab, and the third column of whatever our file we're working with, which is hopefully, now we're seeing kind of nice things we could do to a file in kind of useful ways. So if we remember, we have this GTF. It's a file for our human genome that has a bunch of information about gene annotations in it. And if we remember where that is, so hopefully yesterday, I put it in test. So if we move into test or wherever we put the intro to Unix folder that we pulled from my GitHub yesterday, so we're going to move into that directory. And remember, we had these HG19 GTF. And if we just want to see again what's in that, we could use the command less. And that's a way to kind of see what's in a file that we can scroll through. And remember, there's information about a chromosome number, stuff about annotations, stuff that it's an exon, its start position, its stop position, etc. I'm going to teach us one nice thing we can do with less, because it really annoys me when text wraps like this, because it's really difficult to see what's going on. So I'm going to type Q to get out of less. I'm going to give less a modifier here, and this is going to be the capital S modifier. And this prevents text wrapping. And so now we can actually see or visualize what's in this file in a pretty useful way now. So we can scroll down using our down arrow key, up with our up arrow key, and we can actually scroll over using our side to side arrow keys. And so we can see this is a nice tabular delimited file. We have chromosome 2 separated by a tab, something about where the gene annotation came from. We know it's an exon. We know where it starts. We know where it stops. So this is now the exon start and stop position on chromosome 2. And then there's some other stuff about, where it came from. It's a transcript ID, so we know it came from, RNA-seq data probably, and then some quotes about probably what sort of data set it came out of. And so that's the format of our GTF file. Hopefully that's kind of nice for us. And so we can do lots of things to this in awk. And now we're starting to get into, kind of the fun things we can really do with data. And, it's kind of like, okay, it's tab delimited data. Almost all of our data at some point or another is going to be in, a tabular format. If we're used to doing things in R, generally R is taking tabular data. How genetic data comes to us is generally tabular. Most other kind of processing of different data comes out like this. And so awk is a really useful tool for us. So to get out of our less command again, we just type Q to quit. And we can kind of start futzing around and seeing how awk can be really useful for us. So remember, awk, we give it a command, and so we tell it what we want it to do. And so here we're just asking awk to print the file. And the standard performance of any program in Unix is to print it to the standard output. And so it just is going to print out everything that's there. We could think of a synonymous way to do that. Another way to do that would have been using the tool cat, right? And so if we concatenated HG19, it does the exact same thing for us. It just prints it to the standard output. If we wanted to do, or save what we're doing to one of these commands, we'd use a redirect, right? If we just wanted to pull the first column there, and you can see I'm used to kind of auto completing my commands. I'll show us that one more time because I saved myself from trying to leave off the end of a quote or a parentheses or something. So I did a double quote, went back, put my curly brackets in, and then went back. Ooh, you guys are getting to see my fingers warm up this morning. So we're printing, now here we're gonna print our first column of HG19. And remember, I'm using tab to auto-complete this because there's only one thing that starts with HG in this directory. I'm just typing HG and hitting tab. Tab, and it auto-completes for me. That feels good. And if I do that, I'm gonna print just the first column. And I'm scrolling up now through it. There's lots of stuff there. And I'm scrolling back down. So, there's information for chromosome 2, chromosome 21, and chromosome 3 in this GTF file. It's truncated. It's not covering the whole genome. I can use my up arrow because now we're just going to want to print the fourth column. And so remember, the fourth column of that file is where the gene, the exon region starts, or the gene annotation region starts. So if we wanted to see that again, we could do less HD19. And we can see, there's chromosome number, there's information, we know it's an exon, and the fourth column is where the gene region starts. Feels hopefully okay. If we wanted to know what chromosome and where it starts was, I'm going to do 2 up arrows there. And just to show us or remind us, if I left that quote off and I hit enter, what do I get? Is I get this right caret, and this is basically the computer saying, hey, you started something, you started a quote and you didn't finish it, and it's waiting for me to do something else to finish this command. I can type that caret, and then actually tells me there's a syntax error, so I actually finished it here with that second quote. And it actually tells me where it is. That makes me feel nice that at least the computer is trying to help me. If I do that one more time and I'm stuck that way again, and I don't want to finish it or I can't finish it, remember we can Control C, and that quits that command. So I'm just trying to, reiterate the stuff we've already learned to make it kind of more familiar. So if we wanted to print the first and fourth column, I'm going to scroll up a couple times. So I just hit the up arrow a number of times to get back to the command that I had that I liked. We could print our first column, adding some quotes. I'm adding a tab now with that escaped T in quotes. And then I'm going to print my fourth column with the $4. And I could enter. And now I'm getting the first column, a tab, and our fourth column printed out. Let's see if we're doing all right. That's a good question. Okay. Yep. Yeah. So generally I think awk is 1 index, not 0 indexed. Yep. So our first column is going to be 1, not a 0. That's a very relevant question. Yep. So hopefully, at least awk is. There are situations where if you're using Unix, because you can run Perl or C or other sorts of language scripts through it, that's going to change. Your indexing is going to change, so your first column might be a 0, but in this case, it's 1 indexed. If we hit our up arrow again, helps if I'm on the right thing. We can actually see we can do math in our awk. So, just like in, Excel or something, our asterisk in this case isn't a wildcard, it is a multiplier. And I don't know why biologically you'd want to do this, but here we can print our first column, a tab, and then the product of our exon start position times our exon end position in this file. And so now we're actually doing, kind of fun things in our file. And we get this as a tab delimited output file. So hopefully that's kind of nice. Hopefully that seems pretty fun. At least, now we're actually starting to, I know the first few days have been, lots of, learning and stuff. And now we're actually like, oh, now I'm doing like actual programming. And we can get, pretty crazy with awk. So awk can give you if statements, for example. So I can, like I said, if you can verbally say something in, that you want the computer to do, you can basically find a way to code it, which is just great. So, I can say, if the age is greater than 21, can you print me beer, please? And so we can feed it, a conditional statement. So print those employees who actually worked, for example. So here we have tabular data in a file called employee.txt or emp.txt. So if we want to see what's in there, we can less emp.text, and we should all have gotten this. And we can see, there it is. Oh, so there's just 5. I can't remember how many employees we have. We have a list of employees. We have their wages. So this is from 1992 or something. And then we have how many hours they worked in our third column. 10 hours, 20 hours, 22 hours, 18 hours, you know, whatever. My ice cream shop wasn't open for that long on the pier, I guess, that week. So we want to print employees that worked. You know, I want to know who worked this week. How do we do that? We can use awk. Awk is great. So we can do awk. We have quotes. We have curly brackets. If, and now we're asking if column 3 is greater than 0, print. So we're going to print just those lines that have, you know, column 3 greater than 0 in my employee.txt file. And we've done it. That's kind of nice also, right? And so, yeah, this file only has 6 lines, whatever. You know, hopefully the reason why you're here is because you have files that are, you know, gigs big and many thousands or millions of lines. And so, you know, you can see how this can be pretty useful. We have, you know, another file here called sales.txt. And in that is what we sold. You know, maybe this is a school bookstore, how many of them, and how much they cost. And so we can use awk also to print information about, you know, something here. And so we can not only sort by numbers, we can sort by text here. And so if we want to find lines only on computers, we could awk, curly brackets, if, and now we're saying if column 2, and then we're using a double equal sign, and that means for an exact match. And now we have to put it in quotes because it is text, computers. We'll close that out, print. In the sales.txt file. And so we've now selected just those two rows. And hopefully, you know, we're thinking now, and there's always a lot of ways to skin a cat in Unix. And hopefully some of us at least are going, oh, there's another way I could have done that. And that is correct. So how would we have done that? I'll give us 15 seconds to make sure our brains are awake. And hopefully one other way we could have done that would have been using grep, right? So I could have grepped computers in sales.txt and hit enter, and I get the exact same thing, right? So hopefully that feels good if we were thinking that. So, you know, there's lots of ways to do things in Unix, and different people prefer different methods of things. If you, or hopefully when you are, you know, starting to Google your own questions for your own, you know, issues or your specific data types or your specific, you know, computational needs, you're going to find there's folks on like Stacks Overflow or these sorts of websites that really compete with their favorite way to do things. And so they'll do things like, you know, clock how long it takes someone to, you know, use to do a process using grep versus how long it takes to do a process using awk. And there's, you know, people that, you know, really have favorites. And so like they'll think of some, you know, crazy grep way to do something that you could do in awk with a one line or vice versa. And there's, you know, there's a lot of, you know, people like this stuff. So you'll find all sorts of different ways. And so there's, lots of different solutions. And, you'll find one that's hopefully right for you. And then someone was asking what happens if you only put 1 equals. You mean without the $sign? It won't know that you're working with a column. And, that's kind of, let's see. As opposed to a double match. I'm honestly not always positive. I think, I don't know. Wow. That's what happens. It repeats it a bunch of times, and I'm not sure why that is. Yep. So I'm honestly not sure. And that's something else that oftentimes, I don't know all of these things. I'm not sure of exactly how all these things behave. So, often, my answer when I'm not sure is, I don't know, try it, check it out. And so here it actually looks like it just replaced column 2 for computers, as opposed to, so this would be actually akin to us setting out, everything else for computers. It actually replaced what was in column 2 for computers for everything, which is kind of interesting. I actually didn't know that would be the behavior. And that's one reason also why it's really nice. And like I suggested before, if you're not sure of how your code's going to work, or you're not positive, it's always useful to kind of have a little dummy file that you can test it out on to make sure it behaves as you want to before you start, using real computational resources to process big files, given a bunch of time. Yep. Oh, yep. Nathan knew. Thanks, Nathan. Yeah. So, we can, practice and do a bunch of things, right? Sorry, my dog's being a pain. So we can see how it behaves with lots of different things. So if we want, back to our HG19, if we wanted to grab only those genes that start, within greater than 50 base pairs from the beginning of a chromosome, we could do that using this first statement. I'm gonna make sure we're all with me. Yep. Okay, cool. And so if we want to try that, we could do, so we could say, awk if column 4 is greater than 50, print. And so it'll print everything where column 4 is greater than 50. We could, use it just like we'd use grep before. So we could grab just those things that are on chromosome 2. So if, and I use the up arrow, column 1 is equal to chromosome 2, print. And so now we only got what was on chromosome 2. And again, we could have done that with grep. And then we could do awk if you're on chromosome 2, and now we're making our print statement more complicated. So if you're chromosome 2, please print column 1, a tab, column 3. So now I'm printing, you know, column 1 and column 3 only for chromosome 2. And so that's telling me we're on an exon. And so we can make these statements pretty complicated and fun if we want to, right? Yeah. And so what, for example, if I only want genes longer than 500 base pairs, could we do this? How about only genes that are longer than 500 base pairs on chromosome 2? And so hopefully we're kind of thinking about ways we could do those sorts of operations ourselves. Sure. All right. Okay. We're looking good. So hopefully we can do that. And so, you know, if I only want genes that are larger than 500 base pairs, we can actually do conditional math in our awk if statement, right? And so I could write awk if, grab my curly brackets, if column 5 minus column 4 is greater than 500 base pairs, print. In HG19. So now I'm only selecting exons that are larger than 500 base pairs. You know, maybe I only wanted them if they're on chromosome 2. And so there's a number of ways you could do this. So one of those is using a double and sign. So I can write if column 1 is equal to the text file chromosome 2. And then I'm using ands, 2 ands, column 5 minus column 4 is greater than 500, print. And so now I'm selecting only those genes that are larger than 500 base pairs on chromosome 2. And, you know, we can do that. That feels pretty nice. You know, this is now we're starting to get in the sort of thing where hopefully, you know, if your PI or something goes like, hey, can you tell me how many genes are larger than 500 base pairs on chromosome 2? And you're in like a lab meeting. What do we do then? Then we just pipe that into word count minus line. And we know, at least in this file, we have 110 genes. And now we look, you know, really smart in front of somebody in a meeting, maybe, if that's the question that was asked and no one else knew the answer, right? And so we can do this sort of stuff. And now we're starting to get into things that are hopefully, you know, relatively biologically relevant or useful. You know, we could have done this another way, you know, depending on what you prefer. So we could have also grepped. And here we're saying lines that, remember, because our file is kind of complicated, we're grepping only those things that start with chromosome 2. And now we have an escape S. So now we're grabbing all lines that start with chromosome 2 and then have a space. And so we're now not including chromosome 21 or 22 in HG19. And then we can pipe that into awk, into a conditional awk statement where we might say if column 5 minus column 4 is greater than 500 base pairs. Print, and I forgot I opened another parentheses. And we could do that as well. And that does the exact same thing, right? And so hopefully we feel pretty good. And I think we should, and you can string many pipes together. And so here I just piped the answer of that into word count minus line, and I got the same thing, 110 genes, right? And so you can string all these commands together. And that's one of the really useful things about Unix is every single kind of command or program in and of itself maybe isn't super powerful, but it's actually designed to be very modular and work kind of back to back to back like this. And so that's one of the really powerful things is as you learn more and more tools, then you can do more and more complicated things by stringing series of commands together. And so hopefully that feels pretty useful. And make sure we're doing all right. Yep. All right, I think we're okay. I hope we're okay. Double check. All right. Yep. All right. Nice. All right. And so, here we can see, we're kind of doing, and that's kind of, I think people in the chat are kind of, coming upon this, here with grep, we're really searching by lines, and with awk, we're searching by columns. And so, grep is a line searcher, and awk, at least in this situation, is more of a column tabular sort of searcher with our data. And that's kind of what we did here with our second command. All right. With awk, we can do other stuff as well. So awk, like I said, is kind of a tabular data processor, and it performs tasks for us. It's a program. So for example, we can use awk and sum to calculate the sum of a particular column. So I could say awk sum, and here I'm actually, sum isn't a function itself, but I'm creating a variable that's going to only exist for as long as this code is. So in this situation, sum is acting not as a function, but as kind of a temporary storage. I'm using plus equal, which means add the value to the variable sum, column 2. End is going to do it to the end of the file. And then we're going to add another function for awk here. And this time we're printing sum, the variable we just started, in our employee text file. So, like I said, sum's not doing something, but the command equals plus is doing something. And here we're just calling it sum. And so if we remember, employee.text has names, wages, and so this is how much folks make and how many hours they worked. And so we're going to print kind of the total amount of how much everyone makes in that whatever ice cream shop. So now I'm saying sum. And now then I'm going to print that function. In that file. And so now we're finding, if everyone was working at the same time, how much money would I be spending per hour on wages? And just, make sure we're okay on the chats in a second. And just to kind of prove the point that sum isn't doing anything, maybe it was, maybe I should have just called it box or something. I could say awk, start a variable called box, to box, add, plus equals 2, and then print box. And it would do the same thing. And so here sum's not the function, it's the variable I'm creating. And so, like I said, variables are like boxes. Here we're basically creating the variable where we're saying put everything in column 2 into that box to the end of the file, and then we're printing it. So we're doing it to the end of the file, and then we're printing our answer, right? So hopefully that feels sort of okay. Cool. Yeah, and you could, so people are asking about subtraction or multiplication. You could do it as long as it makes sense. So that's a good question. So I believe, yeah, so I just changed this to minus equals 2, and I get the, minus 26.5. And so maybe that's what I care about more. I care that I'm actually losing $26.50 an hour if I'm the employee here. Yep. And yeah, and some in this case is temporary. It only exists for as long as the script is running. And we'll kind of see that a little bit more when we're creating these variables in like shell scripts in a little bit. And so we'll kind of see how that works. So we can create a bunch of different variables that basically only exist for as long as this is running. And so if we wanted to save those, we have to redirect that to an output. So let's, try a couple of these. So maybe actually care more about how many, oh yeah, we can, I guess if we go back to our HG19 file, we can, sum the base pair start position of all of our exons. I'm sorry, my dog is whining. So here I'm going to just call it sum, or if I wanted to mix it up, I'll call it, base pair start or something, whatever I want to do that's, easy and, rememberable for, that given moment. I'm summing column 4 to the end of the file, and then I'm printing base pair start. And that's what we get for that file. Yeah. All right. I like that you guys are experimenting. That's exactly, what I would do, or how, I figured this stuff out. For the most part, we're all in this because we have data that we want to do things that are useful and fun and important scientifically with, but we don't necessarily need to be all, insane programmers. And that's, why we're doing this. And, that's kind of how I think lots of us, in the collaboratory at least, are here, or how we got started is we're all just kind of self-taught by experimenting, and we had a need that we had to fix or fill. And so, that's kind of how we're here. I think that's great. All right. So we can learn another kind of useful awk command is nr, which means the number of records, which is, here the number of lines. And so, for example, if we want to know how large a file was, or how many lines a file was, I could say awk to the end, print nr. And so that's going to give us our line count column, right? And so here that file has 3,000 lines in it. And so here I'm saying awk, go to the end of the file and print the number of records in this file. And hopefully, we're thinking that there's another way to have done that, which would be HG19, or with word count, minus line, or flag line for how many lines there are, which is nice. And then we can, make these more complicated, like I said. So we could, for example, do things like, we could you know, we want to know the mean start position of all the exons in this file. We could do that. So we could, you know, awk, and here now we're going to sum plus equals the start position of our chromosomes, or of our exons, to the end of the file. And then we're going to print sum, and then perform an action on that variable now. 3,000, because we know there's 3,000 lines there. And so now we're finding the mean start position of the exons in this file. And it gives us an answer in scientific notation, which is kind of annoying, but at least we have an answer. We'll talk about how to fix that in a minute. There would have been another way to have typed that, right? Because we just learned number of records, as opposed to summing by 3,000 if we didn't know that number. And maybe we wanted to perform this task over bunches of files, and we'll kind of learn about how to shell script that in a little while. We could have done it by print the sum over the number of records, and it gives us the same thing, right? And so that's really useful if we don't know how many records are in a file, or how many, you know, column, how many, you know, how many records are in that file, which is kind of nice. We can make this really, really complicated if we want. So for example, you know, here we're going to ask if we're on chromosome 2, then we're going to sum, we're going to create this variable sum. We're going to add up the start position of all those, of all the exons to the end, and then we're going to print that, right? And so now we're making these things pretty complicated. So awk if the first column is equal to chromosome 2, sum, we're creating a variable now, add up the start positions of all those exons to the end of the file, and then we're going to print the variable we just made, called sum in HT19. And then we've done that. I think, all right. I think Nathan, yeah, I think Nathan's answering all our questions. So thanks, Nathan. But I think we're in pretty good shape. And then in a second here, we're going to do one more function, and this is going to be to how to not have our answer in scientific notation, and then we'll kind of take a break as we're going to be done with awk, and then kind of sort on to the next thing. So if we remember, we were using our up arrow key a couple of times, and here we're going to add, as opposed to print, we're adding printf. And remember, we saw that earlier when we were, I guess on day 1 when we made our large text file, and printf is just print format. And we're going to add now, we're going to tell it, and I'm honestly not sure exactly what that syntax means. I learned it at some point, and I forgot before being here. We're saying something about, here we're going to print our answer, but we're formatting the answer to go to some significant number of digits. And so now we have our answer that's not in scientific notation anymore. And I think this means, oh yeah, it's print if, and then we're saying we're going to allow 8 digits before a decimal and 3 after. And then we're going to give it a new line. And so that's what we're doing here. And so that's how we changed our answer from, 9.98 to the 6 to whatever this is going to be, 99. I add 9,900,000 on and on, right? And so that's how we're at. And so we can fix this. And like I said, how did I learn this little function? Is I wasn't sure how to get rid of that scientific notation, and it bothered me, and I Googled it, and then I tried out different things for our significant digit function here, and that's how I arrived at this answer. And I'm sure there's lots of other ways to get there, but hopefully that's kind of a decent start. So hopefully we can see that awk is pretty useful for us and could potentially be a nice tool we'd want to use. And so we're going to go on with some other tools, sort, but I'm going to propose that we take a 5-minute break and maybe, allow us all to stretch, refill our coffee, and get back at 10 o'clock. Hopefully that works for us. And maybe we can answer questions, or for folks that need to catch up, we can pause for a second and allow us all to do that. So hopefully that works. So our next useful tool is sort. And sort's nice because it rearranges our file. So things are sorted, and we can use sort to sort things both numerically and alphabetically, and that's pretty nice. So the general syntax of sort is sort whatever options we want in our file. Sort flag n sorts numerically. Sort flag k allows us to sort by a particular column. So if we remember, we had our file regular expressions that had, beet, brat, boat, bat, and banana in it. We could sort that if we wanted to. So I left it, and then I Q to quit. And now I've sorted this alphabetically. That's nice. We could sort a file numerically if we wanted to, and it actually will still sort it alphabetically in this case because there's no numbers in it. We can sort by columns. And so remember, we had our sales our sales data. And so maybe I wanted to know, sort it alphabetically by what those objects were. So in that less sales.text, we have clothing, computers, textbooks, clothing, computers, supplies, textbooks, but it's all out of order. Maybe I want this to be alphabetically set up for me. So I'm going to Q again because I left it. I could sort flag K to sales.text. And now I've sorted this alphabetically by my second column. I can add specific modifiers to this. So maybe I want to sort by the price or how much sales there were in each of these quarters or months or whatever. So I can sort K by column. I'm going to now sort by column 3, and I'm going to sort column 3 numerically. And so now I've ordered this file numerically by the third column, which is pretty nice. Another pretty useful tool is unique. And this is going to remove duplicate lines from a file. And it has a very similar syntax to sort. UNIQ, options, and input. And we can do fun things with it. For example, we can count how many times a line occurred, or we can print only duplicate lines, the flag D. And unique is interesting or particular in that it assumes the file is sorted. So how it works is it says, this is what's on the first column or the first row. Does the second row match that? And if it doesn't, then it will keep both, or depending on what you do. If they match, then it counts them as a duplicate. And so you have to have a pre-sorted file for Unique to work. So we have a file called numbers.txt that has a bunch of numbers in it, or a handful of numbers. 3, 7, 7, 4, 5, etc. If we want to know what's duplicated in that file, we can use unique. But we have to do something first. We have to make sure it's sorted, because we know this file is not sorted, right? And so how sort works is it goes, does 3 match 7? No. Does 7 match 7? Yes. Does 7 match 4? No, etc. But it would miss the fact that there's another 7 here and another 7 here, because it's not a sorted file. And so we could find out how many unique lines are there, for example, given with a number of different kind of methods or ways. The first of which is we could sort numerically numbers.txt, and then we're going to redirect that to something we're going to call numbers sort.txt. And so now we've written that file, numbers sort.txt. And now it's sorted numerically, and all our 7s are at the end. Then we could run unique on numbers sort.txt and find that. And this is just going to be the unique numbers that are there, 1 through 7. We could also use pipes to do this without creating an intermediate file, which is nice. So I could sort numbers.txt and pipe that into unique. And I get the same thing, 1 through 7. If I wanted to know what was duplicated, I could run unique d numbers sort. And remember, I'm typing that quickly because I'm using my tab. And I know that 7 is duplicated because I've asked for what's duplicated there. So I know I have at least 1 7. If I want to know how many times there is a 7 there, I'm going to go up arrow and change the D to a C. And now it's going to tell me how many times each one of these characters occurs. I have 1 1, 1 2, and I have 4 7s there. Hopefully that feels all right. So you have a bunch of commands you'd like to automate. You can put them all on separate lines of a file. That's great. And you can put them into a shell script. And the shell script is what we did earlier when we made the script to get an interactive session. That's a shell script. It's basically a file that contains something we want to execute. And we can make them kind of, as complicated as we want and do all sorts of fun things with them. So if we wanted to automate any of the things you've learned so far before or anything else, we can put them in shell scripts and have them run. So you want to use a text editor to write your shell script. You don't want to use something like, Word, Microsoft Word. You want a text editor, so you could do it in Nano or V or Vim, or you could write it in, Notepad or your favorite text editor on your computer. And then after you write your shell script, you need to change the permission of that script to make it executable. And that's what we're going to do. And so, now it's actually not my first script. It's going to be our second because we've already done one, but we can do that. So if we nano script.shell, and it doesn't actually need to end in .sh. That's just general syntax, just like a doc is for a Microsoft, Word document, for example. It's just kind of standard syntax to let you know what you have in that is going to be a shell script, something that's going to be executable. It doesn't necessarily need to be that. So you could write nano script with nothing, or nano script, blah, blah, and it would perform the same way. Those are just useful things to let you know what you're working with. I got an error. So here I have it. And now what I'm doing is the top of my line is going to be, or the top of my file is going to start with what we call a shebang. And this is a hashtag exclamation point. And then I'm telling it how to interpret what is going to follow. So here I'm saying, you're going to read, computer, please read what's coming next with the bash language, which is what we've been typing in so far, that's stored in the bin directory of my computer. And so if what you're writing is bash, you don't actually need this always if the default language of your computer is also bash. But it's good practice to put there. And if what was coming next, for example, was going to be not written in bash, which is what we've been writing in so far, which is born again shell, which is kind of the general terminal language of Unix. If the next thing that was coming, for example, was going to be written in the language of Python or Perl or C, I could actually change this to say bin Perl, and the computer would interpret what follows as Perl, not bash. And we're going to use the command echo. And remember, echo just prints the standard output of whatever follows. And I'm telling echo to repeat my first script. And I'll exit, and I'll save. And I want to save it in the same name. That's great. And, like I said before, like here I'm hitting, you can't see me, I'm hitting tab repeatedly. It's not wanting to autocomplete script.shell because script.shell is not executable at this point. We can make it executable using the change mode command, and we're changing the mode so that you, the user, which is, in your group yourself, can execute script.shell. Now I hit /script.shell. And the answer is my first script. So echo performed its task in this script. So hopefully that feels pretty good. We can do lots and lots of things in that script. So let's create a script where we're going to split this GTF file into files corresponding to every chromosome. And so I'm telling you right now, there's chromosomes 2, 3, and 21 there because it's truncated. And save every file into a separate directory we're going to call chromosome. And here's the syntax, $, curly brackets, I, for the placeholders of 2, 3, and 21, GTF. So we can do this. And if we just want to nano that first script again, I should have done nano script.shell. So here it is. I'm just going to edit this again. And so now we're putting a bunch of commands here. So we're going to use the commands that we've learned: make directory, chromosome 2, GTF, make directory chromosome 3 underscore GTF, and make directory chromosome 21 underscore GTF. And then we're going to do tasks that we've learned. So we're going to grep chromosome 2, by a space in the first column. And sorry, not the first column. Here, the $1 means it's a symbol for there's going to be a file fed to you, and that's what that is. I'm going to put that in chromosome 2 GTF in a file called chromosome 2 GTF. So here we're saying this script is going to expect a file that's going to be fed to it, and that's what this $1 means. We're going to grep chromosome 2, and we're going to feed the output of that grep into the directory grep2 GTF that we're making above, right here. And then we're going to save that into a file called chromosome 2 GTF. And if we wanted to, so let's type it out. So we're doing the same thing for chromosome 3. Oh, and I, of course, put an egregious typo there. So this should say chromosome 2, chromosome 3. We'll do the last thing. Oh, I'm typing all sorts of fun typos today. All right, and so that's going to be everything that's here. And so this should now split that file into 3 files, put them in appropriately named files and appropriately named folders. If we didn't want to echo my first script because we're sick of seeing that or whatever, we can comment out that line. And you can comment out any line in a script. And what that will do is not execute what's on that line. So, for example, if I wanted to annotate my script so I could name or, remember what I'm doing, I could use a hashtag and say, here I'm making folders. And then I could write up here, here I'm splitting the GTF or whatever, and so it's nice. You can use these hashtags to remind yourself what you're doing inside of the script. We're going to save it, and then we're going to run it. And I think that means I probably have a typo in there because it should have completed already. So it probably means I forgot a quote. Should be all right. Maybe it takes longer than I thought. Oh. Oh, thank you. Yeah, that works. Yeah, I didn't feed it a file, of course. So that's why I got stuck. So Control C again. I'm going to remove those directories because I don't want them, but we have to. And I'm getting asked these questions because I changed my RM to protect myself. Yeah, and I completely forgot. We need to feed it a script, or feed it a file, which is what we expected. So I need to feed it hd19 GTF, and it ran. And that's how long it should have taken. And so if we type ls, we can see we've created 3 directories: chromosome 2, chromosome 3, and chromosome 21. And if we cd into one of them, we have a file. And if we look at what's in that file, it should be the lines that correspond to the appropriate chromosome. So then we should feel pretty good about ourselves, hopefully. So, that's kind of the basics of shell scripting. And so now we're going to get into how to do or call programs on Hoffman. So there's kind of different ways we can run programs. And so, of course, most of us aren't going to write all of our own complicated scripts and programs to do everything we want. We have tools we want to use that are going to do things for us on Hoffman. And there's a number of different ways to call programs on the Hoffman cluster. One of them is you can install something locally and call that program. So if I want to run GATK, the Genome Analysis Toolkit, I can install it on Hoffman in my home directory and call that GATK program. And since GATK is a Java executable jar file, I would have to call it using Java, how much RAM I want, and here it'd be asking for 4 gigs of RAM. I'm telling it I'm feeding Java a jar file, and then I'd have to tell it the exact path to wherever I keep GATK on my home directory, right? And so that's one way to call a program. I'm gonna make sure we're okay up here. Oh yeah, so someone was asking, is the bin bash also commented out? And it's not, and I don't know why. I'm honestly not sure why the hashtag exclamation point, the thing called the shebang, is, or some people call it hashbang, and I'm honestly not sure why that's the right syntax. And I've actually tried to look up why it's even called a shebang, and there's like a whole mired history that no one agrees about on the interwebs of where the origin of that is or why it's called that even. So it's something that just dates back to the founding days of Unix from the late 70s or early 80s, and it's just kind of been with us for that way. So that's that. Yeah, so, or maybe someone else knows, maybe Nathan knows, honestly. So that's one way to do something. So if you have programs you can download and install, you can put them onto your Hoffman cluster and run them. You can also use preloaded modules on Hoffman. And if I want to do that, I would use the command module load GATK. And what this is doing is taking the version of GATK that's loaded on Hoffman and bringing that into my local environment. So although they've installed the Genome Analysis Toolkit on the Hoffman 2 cluster, it's not available to me until I load it. And you can load also programs at the top of shell scripts, and I'll show us how to do that. Or you could make a profile to load local programs, and then you can source that. And this would be like sourcing our bash profile and bring that into our local session as well. And so I could have the loadings of programs in something called like a GATK profile, which would be another script, and I could source that, and then it would bring where I want, or where the position of all these things is in the directories, to my local session and allow them to work. And so there's kind of different ways to do these things. And depending on what you want to do, you might want to use kind of different methods for these things. And so, for example, if version control is really important to you, meaning you want to be able to use the exact version of a specific program you want. And this is, oftentimes, if you're using like the Genome Analysis Toolkit, there's a new version released every couple weeks or month. And maybe you want to use the most recent version, or you want to use the same version that collaborators are using or something else, then you'd probably want to load your own program. If you care less about that, you could use the programs that are installed on Hoffman. And so we have environmental modules, and these are on Hoffman, and you load them using the module load module file. And we can see a list of all those if we go to this website, or we can type the command module available. So if we see module available, it'll take a second. It's going to print out all the different programs that are available on Hoffman that are already installed there. And it'll even tell you the default versions of things that there's multiple versions installed for. So if you want to use bed tools, there's a bunch of different versions installed, and it tells you which one you'd load by default, or you can specifically load an older version or a newer version if you wanted to. And the reason why many of these things have multiple versions installed is because, maybe 6 years ago, someone said, hey, it'd be really helpful. They emailed the Hoffman folks and said, hey, it'd be really helpful if you could install bed tools. And they installed this. And then maybe a year later, somebody said, oh, there's been a major update to bed tools and it fixed these bugs. And the Hoffman folks said, okay, we'll install that for you. And then, maybe that's happened repeated times. And so if you want to install or load a specific version, you can, using module load bed tools. And then if you want to install a specific version, you can do that as well. But you would have to call that version using by specifying which one you want. So hopefully that makes sense. And these are all going to be kind of examples now that are specific to, me because, or to genetic analyses, because that's what I generally work on. So, if I want to use the program BWA, Brown's and Wheeler aligner, or Burroughs Wheeler aligner, I can do that. But if I type BWA, I get the error command not found. If I type module load BWA, I don't get an error. And then if I type BWA again, I get the BWA kind of, hey, you called me and didn't tell me anything to do command, which is nice. So now it's here. And, it actually tells me, this is how I get the manual if I wanted to, for example. So that's kind of nice. So now BWA is loaded into my environment where it wasn't before. So how do we run a program on Hoffman then? So far, we've been kind of doing these kind of quick, peck and sort of things, which is fine if we want to modify, text files or do different sorts of stuff. But sometimes we're going to want to run things that are going to run for hours or potentially days, and they're going to use lots of RAM. And we're not going to want to have to sit here with my computer open. I can't shut my computer and get on the bus because I'm running BWA to align my reads or something like that. We want to be able to submit jobs to Hoffman, real jobs that we care about, and have them run while we are doing other things. And so we can submit jobs to the queue using a command like this. And so as opposed to asking for an interactive shell, the command's a little bit different. It's queue sub. And then there's lots of different flags that we can use for queue sub. These are going to be kind of my favorites, and I'm going to break them out for us. The first is flag keep working directory, CWD. And so that means the path of where I've submitted the job is going to be proportional to or remembered when the job actually starts running. So if I were to have this flag now, and I said, I wanted to run a script, and right now I'm in, chromosome 21, GTF, the paths for everything in that script are going to be relative to where I'm at submitting that script itself. So that can be helpful. I'm going to use the flag capital V, which means keep these environmental variables, which means if I've loaded BWA, it will remember BWA was loaded when the job actually runs. If you don't have that and you're, for example, calling BWA in your script, it won't work. I'm going to ask for mail at the beginning, the end, or the abortion of a job. And so this is going to actually shoot me an email when the job starts, when it ends, and when it ends if there is an issue. I can name the job if I want to. And then I'm going to use the flag little l to ask for data and to ask for time. So here I'm asking for a job to run with up to 4 gigs of data and for up to 24 hours. And so hopefully that's pretty straightforward. So how do we run a program on Hoffman? Kind of talked about that. If we want to see what's in the queue, we can use the job queue stat. And this lets us see what's trying to be run. And so if I hit queue stat, it's going to print everything that's in the queue and who's actually trying to run it, what they're trying to run. And then it tells us stuff about what's happening. So here's a job that was submitted, and these are now in the queue by QW. It'll change to, if it's too long, it would change to run it when it's running, or it'll give you like an error message. I think I think these ones are errored out. And so that's everything that's going on Hoffman. If we want to see just my jobs, I can do qstat -u and then type my name. And here I don't actually have any jobs running, although it does tell me right now that we're running. And this is an interactive session, the QR login, because that's what we asked for. And so this is telling me I'm running an interactive session right now. Once you're done running a job, we can run the script queue account -j and then feed it a job ID, and the job ID is going to be here. And this tells us how much resources a job used. And so this is really useful. I think someone yesterday was saying, how do I know how much to request? And so it's useful if you're running something for the first time to say, if I want to run BWA, I want to, align a bunch of raw data. Maybe I run BWA on a single file. I see, and I ask for, more resources than I think I'm going to need, more RAM and more time. And then I see how much it used using this command, the queue account. And then I know to request the appropriate amount of resources next time. And you always want to request a little bit more RAM and a little bit more time than you need, but you don't want to way overkill it, because the cluster's queue system won't run your job until it has the resources that it thinks it can run for what you're asking for. And so if I just write always that I need 100 gigs of RAM and 24 hours, that job is going to get kicked way down the queue, because Hoffman doesn't think it can just use, give you 100 gigs of RAM all the time. And so you want to be appropriate. And so there's different places to get help as well for where we want to run these jobs. So there's lots of different resources for how to run jobs, depending on how complicated you need them to be and what resources you want. So here, for example, is Hoffman's the Center for Cognitive Neuroscience, how to submit jobs, and it's telling you a bunch of information for example scripts for how to run things, which is nice. If you want to run batch jobs, here's a bunch of information from the Hoffman 2 website. And so these are going to be things potentially that you want to run serial jobs or serial jobs in arrays, or maybe you want to run jobs that are multi-threaded, for example. So you want to split your process over 10 processing cores. And all those have specific ways you want to ask for those resources. We're not going to go into them. If you're, at that point, hopefully, you can look at this and figure it out. So these are things maybe multi-threaded. And then here's, a bunch of different resources for Hoffman as well on their FAQ website. So, here's a bunch of different stuff about how to submit different jobs, or how to bring things into my path or my environment, etc. Make sure I saw. Yep. So that's a really good question. So folks are asking about if you don't ask for enough time or enough resources, what happens? So Hoffman and most other high performance computing clusters are pretty strict about that. So if you, at your maximum amount of time, if you only ask for an hour and your program needs 3 hours to run, it's going to kill that process after an hour. And unless your program is specifically written to pick up where it started off, and there's a few situations that I know of, at least programs are, when you rerun that program, you start all over again from the beginning. So there's a few kind of Bayesian phylogenetic methods that I know that take literally weeks and weeks to run. And so because they realize people are running these in high performance computing clusters, they pick up where the Markov chain stopped the last time around. But generally the behavior is, if your job gets killed prematurely, you have to start over at the very beginning. And Hoffman has a general 24-hour time limit. So if you have something that's going to run for more than 24 hours, there's ways to get around that. One way is you can buy nodes on Hoffman, or your lab group can buy nodes on Hoffman. And so those will be nodes that will preferentially get used by your group. And when your group uses them, then they will kind of allow for extra rules for those nodes. If your group isn't using them, then they kind of become part of the general clump of available nodes to be used. That's one way to do it. If you have a one-off situation where you need to run it, my understanding is you can email the Hoffman administrators and say like, hey, I need to run this one thing, once or twice, and it takes more than 24 hours, and they'll give you a special little code for it. So hopefully that's helpful. Yeah. All right. So, if we want to see how this might work, let's check it out. So here, I've provided a shell for us that should be in that intro to Unix. And so if you're following along with me perfectly, then we're right now in chromosome 2 GTF. And so we should be able to go back one directory. And in this directory, you should have a shell called BWA shell. And if we nano it to look at it, I can show you what's here. And what we have is we have our shebang. So I'm saying interpret everything else with bash language. The next line is necessitated by Hoffman if I have not loaded a module, but I want to load the module in Hoffman. You have to add this line here. It's basically saying go to ulocal modules defaults init modules.shell. And then I'm saying load module load BWA. So I'm basically loading the shell script, module shell. I'm loading the module BWA. And this is how I'm getting BWA loaded within my shell script. And the other way, if I didn't put this here, would be to load BWA. And then when I submit that job, I'm going to use the flag capital V for keep my environmental variables. And if I haven't done this, my next line won't work because the computer won't know what BWA is to run it. And then the last line is actually my line of code. And so here I'm using the Burroughs-Wheeler liner, which is what we use to map raw sequence data to a reference genome. I'm using the MEM algorithm. I am giving it a toy reference FASTA, which I've put or given to us also in our intro to Unix. I've given us toy reads, and so these are raw data reads, and then I'm redirecting the output to a SAM file. And so this is going to be my output, a sequence alignment map file for where these raw reads map to my reference genome. Because all of this is really, really small, so it could run very quickly for us. I'm also giving us another command down here, which you probably never really want. And this is the command sleep for 90 seconds. And it basically is telling the program to just wait for 90 seconds. And I'm doing that so we can actually then visualize how our program is running on Hoffman, or we can actually see it in the queue, for example. So hopefully that works for us. And maybe lots of us have raw data that we want to map, and that would be, a potentially real command. So to run a script again, we can we want to submit this to Hoffman. We don't want to run it like that. And the reason why we want to submit it to Hoffman is if, this is a real thing and I was just to run BWA shell, maybe this is going to run for hours and hours. And if I close my terminal or, shut my computer or my, battery dies or something else, that's going to kill this process along with me closing the terminal. And when I submit this job to the queue, it's going to run as soon as the Hoffman computer has enough resources to run the job. And so then I can close my computer, restart my computer, I can work on other things. It's not sitting here with this kind of open terminal constantly running. And so that's really nice. And so we're going to start this job by typing qsub. We're keeping the working directory. And that's important because I'm asking BWA to map my toy reads FASTQ file to my toy reference FASTA file. And I haven't told them where they are. So in my script doesn't have anything about where my reference is or where my reads are. So it's assuming they're in the directory where my script is running from. If I wanted to run them somewhere else, I would have to tell them in my script the path, either absolute or relative, to where I've started that script. I'm telling it to keep my environmental variables. So maybe I've had something else loaded that I liked. I'm going to name this test BWA, and then I'm going to ask for resources. I want 2 gigs, and I want 1 hour, which is way too much still. And then I'm going to tell it I want to run BWA shell. And it'll take a second, and then it's telling me my job ID, and it's telling me here's the number, and we're calling it test BWA has been submitted. So if I want to see now, q stat -u, and I'll type my name. So now I'm seeing what's there, and we can see right now test BWA is in the queue. If I type up arrow again, it's still in the queue. Still in the queue. Eventually it'll change to run. Let's see if we're okay. All right, I think we're good. Let's see if we're running yet. Still in the queue. I guess probably 40 of us all just submitted little jobs. Yep. And so there's different ways, we can do qstat u, or we could also do qstat. And I could grep my name. and it would do the same thing. And now we can see I'm actually running this script. And there's few enough reads there that it's going to run for 90 seconds, and it's going to run for 90 seconds, not because I wanted it to run, not because it takes 90 seconds to run, but it's because I have that sleep function there. Otherwise it would run really quickly. And if we type ls, we can see that toy reads BWA Sam has been created. And right now it has 280 bytes. It's going to be little. Still running for that hold. Sure, okay. Yeah, so that's a good question about the executability of that script. So Hoffman does not require that shell script is executable, which is interesting. Basically, every other high performance computing cluster that I've worked on does. And so I don't know why Hoffman doesn't, but it doesn't. Yeah, so that's a good question. All right, so now it's finished running. And then I can use queue account. That should have worked. Oh, I needed a job ID. And then we can see, hopefully I think this will work. Yep, and so I did queue account. So that was QACCT, flag little j. And then I gave it my job name. So in this case, I called it test BWA. And then it tells me everything about how many resources and stuff that job used. So this is nice. And so I can see here, for example, the wall clock time was 92 seconds, which means BWA worked for 2 seconds and my sleep worked for 90 seconds. I can see how much memory was used, how much CPU memory is used. And this is then a nice one. So this max VMem is the max amount of virtual memory that was used. In this case, it used 200 megabytes of memory. And so this is really important. This is an important number that you'd want to use when figuring out how much memory to request for real jobs. So this is where all the stats are. The other nice thing about when we're submitting a job, and I didn't do it here, would be the flag for mail. So when I want mail about the beginning, the end, or the abortion of a job, which we didn't use because I didn't want 3 emails right now, or 2 emails, is all that information about how much resources were used will also be sent in that email to you. And so that's really nice. So hopefully we're feeling, pretty good. And let's see here. Yep. In real life though, I have, data. I don't have just a single file that I want to do something cute on. I just got a bunch of sequence data back from the sequencing facility, and it, totals at, 200 gigs. So, it's a fifth of a terabyte of data, and I have lots and lots of FASTQ files. I don't want to have to submit and change that file for every one of these kind of options, right? And so how do we do this then? Is we can make shells with for loops. And these are great for lots of reasons. Is A, I can submit a single job that will map all these FASTQ files to my reference genome. And they're also really great because it is a nice memory of what I've done to a file itself. And so, if I want, 8 months from now to write my paper and I can't remember what specific options I used to do something, they're all sitting there in my shell script somewhere. And so this is going to be one I'll show us, and you should have this as well. And so I've given us, we've created script. If I did ls any shell script, this is our first script that we created. This BWA shell is the one we just wrote. And then here I'm giving us one that's a BWA loop. And here I'll open it up so we can see what's in it. And and what we're doing, and I've commented or annotated things for us so we can see what we're doing. And so we have our shebang. I'm telling us we're loading the modules we want. And so here's the command to load my module for BWA. And then I want to perform BWA mapping of my raw reads. And here, just like before, we made a variable sum when we were counting employee hours. I'm creating a variable here that I'm going to call reads. And so this variable is only going to exist for as long as the script is running. And it's going to have a specific function. And so I'm saying for, so I'm making a for loop, reads. And so I'm creating a variable called reads in, and so I'm specifying now what I'm creating. And I'm saying for every reads FASTQ. And so reads is now going to represent every file in this directory that ends in reads.fastq, and I have a semicolon, and then I say do. And so now I'm going to perform a function on the variables I'm creating that are called reads. And so reads is going to be each one of the files that ends in reads.fastq iteratively. So it'll find the first one, create a variable called reads, and then do an action. It'll find the second one. It'll store that as the variable now reads, perform the action, find the third one, perform the action, etc. And so I'm going to close this out for a second and just list what's in our file. And so we have toy2 reads FASTQ, toy reads FASTQ, and toy3 reads FASTQ. And so we have 3 files in this directory that meet that condition. And so it's going to do the task 3 times over each one of these variables we're calling reads. Make sure we're doing okay. Yeah, so the variable is only going to kind of exist within this group, So the variable is only going to exist for as long as the do function, or you can see here, I'm ending my for loop with the command done. So the variable is only going to exist for until the done is entered. And so then what I'm doing here within this function is I'm echoing reads. And I'm doing this just because I like to be able to see what I'm working on. I'm creating another variable, and this new variable is going to be called out. And out is going to be equal to, and now these are important. These are the, I don't actually know the right name for these quotes. It's the quote right below the escape key. And it needs to be specifically that sort of quote. And so I'm naming a variable out, another variable, which is going to be, I'm echoing And now the $reads is I'm calling this variable. I'm echoing read, and I'm piping that echo into sed. And in sed, I'm searching for reads fastq, and I'm replacing it with raw map. And so now I'm naming a new variable based on my original variable's name, but I'm changing part of that name. I'm echoing now that variable out so I can see it. And then I'm calling BWA mem. The flag M is just a specific Picard tools issue. Don't worry about it. I'm telling it my reference genome that I want to map to. And then here I have a forward slash, and the forward slash means what comes on the next line should be included on the first line. And so the standard syntax for BWA mem is it expects a reference genome, it expects reads, and then you redirect to an output. And so now I'm saying I want to do BWA mem to this genome. I want to do it for the variable reads, and I want my output to be going to my new output I just named, .sam. And I'm going to do that until I'm done with every file that has reads fastq in this directory. Hopefully that seems okay. Did I just, oh, I just added a Q. That's not good. Let me make sure. All right, and so I'm going to close this, exit. I'm going to say no because I probably typed something dumb in there. And then, you know, in real life, we would submit this to the queue. But in this situation, I'm just going to run it so we can see how it behaves. And it won't run because it's not executable. So we need to make it executable. With BW, with the +X. And here, you notice I left off the U. And the reason why I left off the U is because the default behavior of change mode is to expect it to be just U. And so this works the same way. And just so we can see what's happening, we can run this here because the files are small enough. You would never want to run BWA like this. And it did. And what we can see it did is it ran and it did exactly what we did. I told it to echo everything that started with reads fastq because I had created an environmental variable called reads, and then I said to echo it. So it did that. And then I echoed that name in that script, and I piped that echoed name into sed to replace it. And so then I created another variable, which is called out. And then I echoed out. And then I ran BWA. And this is all the stuff that BWA gives you as output. And then I did it for the next file. I did it for toy3 reads fastq. I renamed the output. BWA ran. And then I did it for toy reads fastq. I renamed the output and it ran. And so if we type ls, now we can see we've actually generated all three of these outputs based on the input name of our file itself that we wanted. And so that should feel pretty nice. So now we're getting to the point of, you know, when we have real data and we have tens or hundreds of files and we want our output to be named based on our input file name or something like that, how do we go about doing that? And this is the way. So hopefully that feels pretty good. We can also, you know, do things that are more and more complicated here. So I've given us one more example, and I'll just open it up in our in Nano. So I've given us a file called bwa loop pipe.shell, and it's almost the same. I'm loading my module file. I'm loading my BWA. I'm also loading a new module or new program called samtools. And I've changed the comment here. So I'm performing BWA mapping, and I'm converting the output from a BAM file to a SAM file. And it looks almost the same, except for the last line, where I've changed my sed a little bit to say something else. And then this line here, so I'm calling BWA mem, I'm telling BWA, here's my reference, here's my reads as input, and then as opposed to redirecting the output to a file, I'm piping the output of BWA into this other program called SAMTools. I'm using this tool called SAMTools, called View in SAMTools, and I'm telling SAMTools it's getting a SAM file and I want the output to be a BAM file, and then I'm redirecting that. So now I'm performing multiple tasks at once, given my genetic data to get a file that's workable for me. And I'm saying done. And so it's doing, I'm just adding things to this script. And so that's, pretty nice. And so you can make these shell scripts as kind of complicated and crazy as you would like, to hopefully suit your needs. And maybe, feel free, if you have a bunch of genetic data, to steal those. Those are actually workable scripts, and modify them as you need to, or, modify stuff as it suits you. And, sorry if you guys aren't, working with raw sequence data. That's just an easy example for me based on, stuff I actually use. So hopefully that works. Other variable placeholders. So we can use, in our for loop, we can add things like curly brackets 1 through 4. And this means we would call all numbers between 1 through 4, for example, in our shell script. And so you could potentially think of ways to like rewrite our first script that we split HG19 out using like curly brackets. Another thing that can be useful is creating a variable that's based on a name, but changing a file extension. And so here we're creating a variable that in this situation I'm calling fn, which in my brain is short for file name, equals to, and then as opposed to, if I created a variable earlier called BAM, as opposed to calling $BAM, I'm calling $ curly brackets BAM, and then the $% means up to, so whatever that name is, up to a period, and then ignore anything that happens after that period with that wildcard. And so this is a really nice way to change file extensions or to add info to files. So oftentimes I'll use this because I like to modify my files based on what's happened to them. So I'll have a variable in a shell loop that looks like this, and my output would be, raw mapped, and then it'll be cleaned, and then it'll be, whatever else I've done to it, sorted, whatever I've done to my file based on the file names for everything that's in a directory, and then I'll kind of change the files based on those placeholders. So hopefully that's sort of useful. And so then I guess we're going, this is a little faster than I thought. Hopefully we're all okay. So for example, then if you want to save your history of what you've typed, if you thought that would be useful, there's kind of one more command we can use, and this is actually called history. And so if I type history, remember how I've been using that up arrow to like navigate through things? History will print the last 1,000 or so lines of what you've typed. And so here's the history of everything we've typed in this workshop so far. And if you wanted to save that, you could. So if that would be useful for you, or if you thought it'd be useful, and most of the commands are in the slides, but if you wanted to save that to try to find something, you could redirect that into history workshop1.txt, for example, and it'll save it there. If you knew you used a command that you liked, but you couldn't remember exactly what it was, you could use history grep awk. And so this will find every instance of awk that we used throughout the course of the workshop, or at least in the last 1,000 lines that you've typed. And so here's all the awk commands we've used. So maybe that would be useful for you. So overall in the workshop, you know, I think we kind of started off with this idea, you know, do all of us need to become programmers? And I really think the answer is no. But it's useful to have, you know, but we want to be able to use these tools to the best of our ability and to improve our ability to do good biology, right? At least my motivation isn't in writing the slickest codes I can. You know, my motivation is in becoming, you know, the best turtle conservation geneticist that I can be. So, you know, hopefully what we've provided is enough knowledge to get you to the point that you can, you know, Google and use manuals and use forums to try to figure out the best ways that you can actually conquer your data. And, you know, you want to know how to do that. You know, I literally, this is what I do is I'll type things like, you know, convert columns to rows in awk and Google. And then you'll see, you know, people have different things, you know, and here's Stacks Overflow, for example, or linuxquestions.org. And there's whole forums of people that are, you know, that are true programmers that like to, you know, help folks out, which is great. And I think it's way better, although these resources are great. I don't think I've ever posted a question to them because I've always, you know, Googled and found someone else asked the same question earlier. So that's also good to know that other folks are wanting to know, you know these things. And so that's great. So unless we have any main questions, I really thank you guys for hanging out. And hopefully the workshop was really useful for you. You are going to be getting, after the workshop ends, a survey about the workshop that's going to come to you from Aloy or the collaboratory. And, you know, please, you know, thoughtfully fill that out if you can. I'll try to, you know, use that stuff to the best of, you know, my ability to modify the workshop in the future to make stuff work well. It's especially kind of goofy given that, you know, this is not in person this time. So we want, you know, trying to make stuff work as best as possible. And then also in 1 second, I'm going to stop sharing my screen. And I'm going to email out a post workshop quiz. It's 10 questions, pretty similar to the one we took at the beginning. And it'd be really helpful to me if you could take that. And if you are taking it for credit, you have to take it. If you're not taking the class for credit, it's helpful for me to see how successful we were at teaching stuff. But I, you know, care less if you take it or not. If you are taking the workshop for credit though, you have to do that. That's how we know you're here till the end, and how we will make sure you get a grade. So for those folks that are out there taking this for credit, please do that in the next, you know, 20 minutes or so. And we kind of have record of when it was completed and that sort of thing. So, you know, hopefully do it. And if you're taking it for credit and you're really worried about like, oh no, I'm going to miss 3 and get a D. That's not how we're grading it. We're grading it more on making sure that, you know, we're hopefully successfully teaching you folks stuff, and that, you know, that you've learned something. So hopefully that seems fair. I don't think we're not giving folks D's. That's not our business. So hopefully that works for us. So I'm going to send that out right now. And then if we have any questions and stuff too, we can try to figure this out. Oh yeah. And all the, yeah. And so if you're asking about workshop credits, this is how we know. And then let's see, I'll send, if folks want their specific quiz scores, once I send it out, I'm going to do it right now. Let me know and I'll give you that feedback. And the class lectures are not going to be emailed to you, but on the collaboratory workshop page for this workshop, all the slides and all the lectures are going to get uploaded. The first 2 days should already be uploaded, and the last one I'm going to email as soon as we finish up here, and it'll hopefully be done by the end of the day or so. So I'm going to email out that workshop right now, and hopefully, or the email out that quiz, and hopefully please take it. And I hope you guys enjoyed. Thanks a bunch.